Hello, Algebra 1 students, and welcome to your new unit. This is topic 7, and the title up here is Quadratics in Vertex Form. The word quadratic is something we're going to talk about later in this lesson, so don't worry if you don't know it. And that is why lesson 7.1 is Introduction to Quadratics. So before we actually start talking about what a quadratic is, let's review something that we've seen both from earlier units. There are 3 tables down below, and your goal is to determine which type of function each table represents. Are they linear or are they exponential? And as a reminder, we do that by looking at the pattern of the outputs over here. So you want to look at the pattern of each of the outputs and see what that tells you about the type of function. So go ahead, take a minute or two, it's pretty quick here, find that pattern between the outputs, and then once you're done, unpause and we'll see how you did. Ready, set, go. Alright, well hopefully you found some success here. You should notice on this first one it has a pretty predictable pattern, doesn't it? It goes up by 2 every time. And we say when you go add or subtract by a common number every time, this is actually known as a common difference. And we say the common difference is positive 2. Actually, later today we're going to talk about how this is known as a common first difference. But we don't really know what a first difference is at this point, so for now we can just think common difference. We should also remember that if you are adding or subtracting commonly between each number, that this is a linear function. Linear functions, of course, make a line. Our second one has a slightly different pattern. You might think at first it adds by 2, which it does, and then you might think, well, plus 2, then plus 4, then plus 6. Wait, no, that doesn't work. You could add 2, then you could add 4, then you could add 8, and then you could add 16. It's kind of like adding by itself every time. And in fact, if you look at that pattern, it also adds by itself every time. It actually follows that same pattern all the way down. So I think there's never a common number that we add or subtract by. And when we're looking for these patterns, we're always going to look for a constant pattern, not a changing pattern. And so if we look for a different way to do this, I think maybe you'll tell that you multiply by 2 every time. Multiplying by 2 is also known as a common ratio. And we went more into that in topic 6, but for now we can simplify it and say a common ratio is going to occur anytime you multiply or divide by those outputs. And our common ratio, I'm just going to say, is times 2. We also learned in topic 6 that this is known as an exponential function. Okay, but then we move on to our last one. And this one might have thrown you for a bit of a loop because you might have tried to look for multiplication first based on this last one, and I think you'll pretty quickly come to a conclusion that there's no multiplication. And then you might have tried addition. You said, well, this one goes up by 1, but then we go up by a different number each time. Well, there is still a somewhat predictable pattern here. And in fact, I would be very impressed if you knew what type of function this last one is, because we haven't talked about it yet. It is a function that is neither linear, and we know it's not linear because there's not the same difference every time. And we know it's not exponential because we're not multiplying by the same number every time. There are actually many families, we call them families of functions, linear functions, exponential functions, in math we haven't learned yet. And each of them have some sort of unique pattern in the outputs. All right, well, today we're going to learn our last type of function for the entire year. Seriously, right? We've learned linear, and then we did linear absolute value and exponential, and this is going to be our last family of functions. However, before we learn the name of this function, I bet you guys can probably figure out a bit about its pattern. So what I have down below is the same table that we just looked at, h of x again. And we're going to go through and actually extend that table, right? There wasn't a 5 or a 6 there. There is over here. So there are 4 questions for you at the bottom. Part A wants you to fill in these 2 blanks. Part B is going to talk about a common second difference. Common, important. Part C wants you to write a formula that says if you know the input, can you make the output? And to test yourself, maybe let's skip up a bit, and then after 6, instead of going to 7, let's say we went to 12. And my question to you is, can you use your formula to figure out what the output is going to be? Last but not least, how come this formula is different than a linear or exponential formula or function? So take about 5 minutes or so to ponder through these, try to fill in what you can, and as always, once you're done, unpause, and we'll come back together. Ready, set, go. All right, let's get to it. Well, to predict these last couple blanks here, we need to extend that pattern out. We saw we went up by 1, then by 3, then by 5, then by 7. And although there isn't a constant value or a constant difference here, there still is a pattern. And a pattern is going to be predictable. Can you see what will go up by next? Well, hopefully you said we're adding by 9, because you might have realized that each of these differences in the outputs are actually changing by 2 every time. And you'll notice, unlike the two functions up above, that even though there isn't a common first difference, there is a common second difference, or there is a common difference of the differences. And that lets us know then, let's see if we can fill this in, 16 plus 9 is 25. It lets us know that this difference will again change by 2, which means our output is going to go up by 11. 9 plus 2 is 11, and it means that our last output is 36. How did you figure it out? I'm just going to draw an arrow up here, and I'm going to say something like a second difference. This guy up above in purple is, of course, our first difference. All right, well, part B should be pretty easy too. We say h of x has a common second difference. Why? Well, and I'm just going to put it's the difference of the first differences. Remember, a difference we always find by just subtracting two numbers. All right, but now part C is interesting, because part C, again, just as a reminder, I asked you to predict or use your formula to say if we went out to the 12th input, what would the output be, right? And we're not just going to simply add 13 here, because that would be for the 7th input. I want to go out 12, and it would be a little bit tedious or arduous to go out 13, and then 15, and then 17, and then 19, and you could get it for 12. Doable. But what if I asked you for the 105th output for the 105th input? Then you really wouldn't want to do that. It would be much faster just to have a simple formula where we use this input, this x, as our only value we substitute in. We do something to that input and it gives us the output. So think, can you see a connection between the inputs and the outputs? And I hope you do, especially based on our last lesson or our last unit, which was that exponential unit. Can't we just take each of these inputs and multiply it by itself, right? Isn't 9 3 times 3 and 16 4 times 4 and so on and so forth? So wouldn't this last guy here just be 12 times 12, which is 144? And the way we can write that formula is we say h of x, the operation given an input, is just the input times itself. Or, and this might be a little bit more friendly for you, instead of h of x, we could just use y, same thing, and x times itself is, of course, x squared. This is a very common formula for this type of pattern, with that square especially. Now, part D asks us to think, why is this type of formula different than anything we've seen so far? And in order to answer that, we should probably look at a few things we have seen so far. So let's start with linear equations. We saw a few examples of linear equations before. In particular, we know if there's an equation in mx plus b, that's linear. We know if we have this mx minus h plus k, that's linear as well. We saw a few more. We saw standard form and a couple others. But yeah, those are our two basic linear forms, though. Notice that these are clearly not this formula because this formula has a square that's attached to an x, and none of these guys have a square. But then you might say, well, exponentials, we used exponents in our exponential section, so it's not an example of an exponential. Well, some exponentials we saw were something like y equals b to the x, or we saw y equals a times b to the x. Or if you wanted some examples with numbers, we saw 2 to the x, or maybe we saw like 3 times 1/2 to the x. And so they do have exponents. But why are they different than this? Well, exponentials have an exponent of x every time. It's an unknown number of times multiplying by itself. Versus this guy has a 2 as an exponent. And what we'll deal with really for the rest of this year, we have 4 units on this type of function. We are going to be dealing with functions that have a square attached to x. All right, so let's flip that page, and without further ado, let's go ahead and see what you guys know about the word quadratic. And you probably don't know much, and that's okay, but we should use some sort of word analysis here. We should look at prefixes. We have the word quad. Maybe you can even, if you speak a different language, maybe if you speak Spanish, you can think about the word quadra. You could think about radic, right? So go through, see if any of those bring anything to mind. And if you know anything else about the word quadratic, maybe your teacher last year showed you some quadratics, let's write those out. Ready, set, go. All right, well, without fail, the very first phrase or prefix that my students always come up with is quad. And they think, ooh, quad, that means 4. And you're not wrong. Quadrilateral, 4 sides, right? However, quadrilateral also has that quadra in it. In fact, most of the times that you hear quad, it's with a quadra after it. And so for those of you that do maybe speak Spanish or another Latin-based language, if I write it like this and I say the word quadra, do you remember what that means? Quadra in Spanish and most Latin-based languages actually means square. Sometimes you'll hear it used in directions too when they talk about blocks. They say cuadras. So we have square here. And in fact, quadra with a Q is Latin for the word square. And that's very important because for now, and we'll expand on this over the next couple lessons, so in the comments, don't tear me to shreds, we're going to say a quadratic equation, or a function, right? Just like this previous page, we had a function and equation, is an equation that has an x squared term. Basically, there is a square attached to x. Quadra, square, kind of makes sense. Now, with any new function, and quadratics are our new function this year, this semester, the next 4 units, we are going to determine how to graph them, solve them, and write them. Today, though, we're just going to focus on the graphing with maybe a little bit of writing. The solving actually, strangely, isn't going to come until the end of this unit. That's kind of backwards what we've done with other units, but that's okay. So let's go ahead and start with how we can graph any new function we get. And that is, of course, with a table, an input-output table. We know, of course, that the x's over here are the inputs. And then we need a formula that turns the inputs into outputs. This formula says take an input and square it. Once you've done this math, you have now transformed an input into an output. Now I have 3 blanks here on purpose, so let's ignore those for now, and let's see if we understand how to make inputs and outputs into points. We have 0, 1, 2, 3, 4, and 5. I picked those as your inputs. And I started to show you the math to transform these into outputs. If 0 is our input, we input it into our formula, and it becomes 0 squared, and then it gives us an output, which I'll show in green, of 0, because 0 times itself is 0. Okay, let's try one more. If we have 1, we input 1 into our formula, and that tells us to do 1 squared. What is 1 times itself? Oh, that's 1. And then traditionally, we write inputs and outputs as a coordinate pair. My input was 1, and my output after I did the math to it was also 1. Now be careful, you might think, oh, 0, 0, 1, 1, the next one's going to be 2, 2, but I think if you ponder this carefully, 2 into our formula means we have to do 2 times itself. 2 times itself is 4, which gives us the point. 2 was the input. When we squared 2, we got 4 as an output. So why don't you go ahead, fill in the rest of these, and then create a graph over on the side. Once you finish doing that, please go ahead and do the 4 questions at the bottom. Right, there's quite a bit it's asking you to do there, so make sure you read through and get them done. And by the end, we should have a pretty good idea of what this quadratic graph looks like. So, good luck, and I'm excited to see your success. All right, well, hopefully you got everything done. I'm not going to run through the math on the rest of these. That would be doing you a disservice, but I am going to quickly fill these in. Inputs, 3, 4, 5. Outputs, we had to square each of those. And then we had to go through and graph. And I'll just graph in blue for now. 0, 0, 1, 1, 2, 4. Some of my students switched the x's and the y's, and they were trying to graph like 9 and 16 and 25 over here. I do my best to make sure that your points that I ask you to graph will always fit on this coordinate plane. So I scale these axes on purpose so that everything fits. So if you're going off the axis, you're probably doing something wrong. All right. 3, 9, 4, 16, and 5, 25. Now, you would totally be excused for thinking that this graph, and I'm going to erase this, would go down and then maybe like this. That's like the exponential that we just studied. However, once you get down to 1, where question 1 asks you to fill in the inputs in the table with the values -3, -2, and -1, you're going to find something different happens. When we use those inputs, and this is important, you don't want to type in your calculator, if you're using a calculator, and you will need one in a bit, -3 squared. The reason why is because you know the right answer to -3 squared. -3 squared means multiply -3 times itself. -3 times -3, that's a negative times a negative, and that is what? Oh, that's right, that is a positive. However, if you type -3 squared into your calculator just like this, your calculator will seemingly lie to you, and it will tell you the answer is -9. But we know it's not -9. The right answer is +9. So what do you need to do to make your calculator tell you the truth? You need to remember last unit. We said we need to take -3, group it in parentheses, then put the square. So once you have that, you should be good to go, and you'll see that your output here is 9, 4, and 1. I'll graph these points in red. -1, 1, -2, 4, -3, 9. And so we actually see that this graph comes down over here, like so, and actually curls like this. Now that's kind of a weird looking graph. I mean, it looks incomplete, I feel like. So we should probably answer these questions to finish off the graph. So we already tackled 1, did that in the table. Do negative inputs create negative outputs for these quadratics? Well, the answer is, I'm going to say not always. In this case, it's definitely no. There are no negatives. And the reason why is when you square a negative, what happens when you multiply a negative times itself? Oh, that's right. The answer is positive. Now, it seems like this would always be the case, right? So if you square a negative, you always get a positive. Well, there's going to be a couple exceptions. We are going to be able to get negative outputs this year just by subtracting something at the end. And then in Algebra 2, you're actually going to be introduced to the idea of imaginary numbers. And then your life is going to take a weird turn, and those negatives may actually give you negatives. All right, now let's jump back to this graph, because I mentioned it looks incomplete. And so number 3 is actually going to help us finish off this graph. And we're going to use the idea of symmetry to extend the graph of our quadratic equation. Where do those arrows go? Well, first let's chat about symmetry. You're introduced to symmetry in art class most of the time, and they may have you fold or maybe even draw a line of symmetry. Sometimes in math, you'll see that line of symmetry with little dashes going through, and that just tells you that you are able to fold your paper, and when you fold it, it will take one side of the paper and reflect it or create a mirror image or flip it to the other side. So can you see that the graph of this quadratic equation, if you flip it to the other side, notice that this little point here is 1, 2, 3, 4 away. So couldn't I go 1, 2, 3, 4 away and make that same point on the other side? So if this is the point 5, comma 25, couldn't we maybe notice that this is the point negative 5, comma 25? That's the reflection of our quadratic graph. And I think once we're there, we can go ahead and finish off that graph. Now I did mention in 3, where did the arrows go? Well, does this quadratic graph stop at each of those endpoints? Well, no, it doesn't. It's going to keep going. We could try -6 or +6. We do need to throw arrows onto the end. And it's important to note that our graph here, and a lot of students will describe this as a U, it's a little bit incorrect to do it like this, because then it looks like the U ends up going straight up and down, and it actually doesn't. We have this U that gets ever wider in each direction. So just be careful about that. This graph is going up forever, but it is also going out or infinitely wide. And that becomes important on number 4 because they ask for the domain and range. So remember, we have a couple ways to define the domain. Probably the better way is that the domain is the list of all the inputs, which means it's a list of all the numbers we're allowed to substitute in for x. Here, I have a lot of inputs, and we were certainly allowed to substitute them in. In fact, you might ask the question, why would you ever not be allowed to substitute in a number? And there are 2 quick answers for you. First, because if you're using a real-life situation, negatives might not make sense, right? If you're building something and you're inputting different lengths to see the price, it probably wouldn't make a lot of sense to input a length of -5 inches. You can't have a negative length. However, more commonly in math, we're actually going to have some functions where the inputs break the function. They cause it to stop working. Unfortunately, we don't have any of those functions this year. So for now, because we're still learning our idea of domain and range, we're just going to say that our domain is all real numbers. We are allowed to use any input that we would like. Now visually what that means is if the domain is the inputs, it's also like it's the x's. And so if we look on our graph, we can think the x-axis goes side to side. And so the domain is actually going to measure how wide the graph gets on the x-axis. And because this graph goes wider and wider and wider in both directions, it gets infinitely wide. So sometimes you'll even see this written as -infinity to infinity. It shows that all of our x's stretch from -infinity to +infinity. This range, though, is going to be a little different. The range is, of course, the list of the outputs. Now, the list of the outputs is going to be restricted or may not be all real numbers based on what's happening to the inputs. In this case, my inputs are getting squared. And we just talked about what happens to inputs when you square them. Don't the answers, the outputs, become positive? So in this case, I think our range, or the y values, are really only going to be positive numbers. However, we should probably look at the graph and apply that same analysis from the width of the domain. The range is not the width, the range is now the height. Well, because of these arrows here, this graph goes up forever. But is there a place where it gets to a lowest point? Well, it's certainly at the lowest point of 10. It goes below that, goes below 5. Here's 0. Oh, I don't think the graph goes below 0. I think the graph gets to 0, There's certainly an output of 0. We have a closed circle here, but I don't think it ever goes below that. And so we can say that this graph has y values that are above or greater than 0, but it also has a y value that's equal to 0. And that's it. The other way you can write this, and it's a little less common this year, is we say we're going from 0 all the way up infinitely far. And we can never quite get to infinity. We use parentheses every time we see infinity. But we can actually get to 0. There's a closed circle at 0. And so to show an equal to 0, we use that cool square bracket. All right, so flipping the page, and we've kind of done the hard stuff now. We've done all of our background knowledge. Now you guys get a chance to practice. You might notice a couple cuts in the video from the previous page. I probably could have smoothed them out a little bit more, but I was really just frustrated with myself. I kept using a name for the quadratic graph that you hadn't learned yet, and then I'm like, oh no, they don't know what that name means, so I had to cut it a bunch of times. But we should probably learn this now. So somewhat of a similar idea. It's not quite the same. When we have a linear equation, the name of the linear graph we usually call a line. When we have a graph of a quadratic equation, the quadra part comes from the equation having a square. The graph, though, is certainly not a square, right? That's kind of a U-shaped graph. The graph has a very special name. The graph of a quadratic equation is called a parabola. Emphasis on the ra. So if you're putting accents on there, there'd be an accent over the A. We don't do that. But either way, we pronounce it, at least in the United States, parabola. If you go to other English-speaking countries in the world, you might hear someone say parabola, which is totally fine. And if you say it in Spanish, it is parabola. Okay, but we say parabola. Why? Because we do our own thing with language. Strangely, parabola is not a Latin word, even though quadra comes from Latin. It's actually a Greek word. And it's Greek because the Greeks are the ones that played around with parabolas the most early on. Now, unlike quadra, which means square and has a pretty practical translation, the translation for parabola makes a lot less sense. And when you guys learn about conic sections or graphs from cones, right? Think an ice cream cone, looks like this. You're going to learn a little bit more about the creation of parabolas. And it turns out that if you cut a cone with a parallel line, like so, parallel to one side of the cone, and then you open up the cone, you look at the inside, that shape is actually a parabola. So that's a little bit of the background, but it doesn't make too much sense to go into it. So instead, let's go ahead and start talking about the graphs of parabolas. Remember, when you graph a quadratic with a square, it will make a parabola. They're connected to each other, and if you call this a parabola, fine, it's not a big deal. If you call the graph a quadratic, it means the same thing. We know what you're talking about. Quadratics, parabolas, very, very similar, very related. So I have down below two tables. Here's our first table. Here's our second table. Your job is to graph each parabola that's going to be created from the quadratic equation. And to do that, because we don't have any shortcuts yet, you are going to have to do a little bit of math here. But the math isn't too terrible. When you do the math, we can either do this by hand or with a calculator. And I'm going to start you by hand because honestly, doing this by hand or doing this with mental math is faster than the calculator. And I always strive to make sure that my students can do, I consider this, basic math without a calculator. Right? That shows me you really know what's going on instead of having a machine do your thinking for you. That's how we achieve better fluency or understanding with numbers. We do them instead of having the machines do them. Then, though, I will show you on the calculator. I will require you to use a calculator because there are certainly some occasions where the numbers are too big or too decimally, we'll pretend that's a word, or too gross. And so you'll want to use a calculator. So you do need to be good with both. So let's see what the heck I'm actually talking about. We have our inputs again, and then of course we have our outputs. And to create an output, we need to replace the input with whatever the value is. So in this case, I'm going to go ahead. You'll want to write a little bit small here. I find myself always running out of room. That's honestly probably too much anyways, but we're going to replace the x with -2. Cooperate pen. There we go. Then we're going to go through and evaluate this expression. To evaluate, we're not isolating a variable, we're just trying to find the value. That's when we go through and we follow PEMDAS, which you guys have been doing since elementary school, and it's important to keep up that practice. It would be silly if you learned something and then forgot it because you stopped practicing it. So, a reminder for PEMDAS, the first thing we do is what's inside the parentheses. That's this guy right here. -2 minus 1 is -3. Everything else, though, stays the same. We're done with the parentheses. Now we're on to the exponents. The exponent says take -3 and multiply it by itself. -3 times itself is 9. There's still a +2 at the end. Then we need to tackle the multiplication. There is none. Division. There is none. Oh, addition. There is some addition here. 9 plus 2 gets us 11. And there's, of course, no subtraction. We're done. PEMDAS is easy. Once we're here, we are going to graph this point. Remember, these points have an input, which was -2, and an output, which is 11. So let's go ahead and get that graphed. We have the point -2, 11 up there. All right, knowing that, why don't you guys go ahead and get the rest of these done? I will show you on the next problem how to use a calculator, but I don't want to keep talking at you. So go ahead, try this by hand. Let's see what you come up with for your numbers, and then we'll check your work. When we check your work, I am going to break out the calculator though, so make sure that you guys have one available. Ready, set, go. Okay, we're back. I went ahead and grabbed my TI-84 graphing calculator. I know we use the TI-30X2S's. But again, I haven't been able to find an emulator for that, and the TI-84 is pretty darn similar. They're both made by TI. If you want an explanation on your calculator, if you use a Casio, which are great, or an HP or something like that, just let me know. But what we're going to do is try to use this and pretty quickly generate the rest of these points. So for example, I'm going to substitute in -1. And honestly, the first one will take the longest. So I'm going to type in exactly what my setup is going to look like. I do require all of my students to show a setup before their answer. So I don't just want to see a number here. I want to actually see what you set up. So parentheses, -1 minus 1 squared plus 2. That's the setup. Once you set this up, then we can go straight to the answer, whether it's mental math, a calculator, or of course you can show more work. And the reason we're practicing this is eventually, once you get to AP Calculus or an AP Math class, you're actually scored on both the setup and the answer. They want to make sure you know what you're trying to do and that you can actually do it. They don't particularly care about the work in between, and so I try to make sure you're prepared for that. So I'm going to type exactly this. So we have parentheses, and then this is where things get weird. Many calculators differentiate or make a difference or a distinction between a negative and a minus. This is a -1, so I replaced x with a, and our negative is down here, -1. Then this is a -1. You cannot put another negative, you will have issues. We will need to do a -1, and make sure you can see the difference. The minus is longer, the negative is slightly higher. Close those parentheses. Then you have two options for your square. One option, which is going to be on pretty much every calculator, is this caret. This up arrow kind of looks like the roof of the house. You can do that guy and then the 2, and that is like a square. Alternatively, many other calculators have this second button. I know it's tough to see. This says x squared, has a second power, and you can hit that and that will give you a square. That's just a shortcut for a square. You'll need this guy for pretty much any other power, 3, 4, 1/2, anything like that. Then we finish with, of course, a +2. All right, we got 6 out of this, nothing to it. So let's go ahead and get all the setups in for the rest of these. Pretty easy to do, and hopefully you've already done something like this before. And then I'm going to show you a couple tricks on the calculator to make this go a little bit faster. All right. Trick number 1. If you hit the up arrow on your calculator, almost all modern calculators have a history. If I hit the up arrow, you're going to be able to go back to one of the problems you already did. Now on the 84, I actually have to hit enter on this to copy it down. You guys might be able to edit yours instantly, and it's just going to look like this. Then you're going to tap your left arrow, and you're going to go back to the one that you want to fix. So I don't want to use -1 anymore. We already did 0. I want to do +1. Whenever you type a number on your calculator, it will automatically delete whatever's there. So if I type a 1, it just replaces the negative with a 1. If you want to get rid of something, use the delete key, not the clear key. The clear will cancel everything. Just delete, and then we're set. When we do that, we end up with an output of 2. All right, well, let's look at one more thing. Let's say that you accidentally delete 2 things at once. Gasp. You delete both of those. You're like, oh no, now I have to redo the whole thing. Well, you actually don't. All calculators come with an insert key that says INS. It's right above delete. And if you do second and then delete, which is insert, it'll start flashing the number, which tells you it's not going to replace the number anymore. It's going to let you insert numbers in front of that. And so I'm going to do a 2, it didn't delete the 1, and then a minus, and now I can go over and we're back to normal. 2 minus 1 squared is going to be 3, and I'll do one more just so I can remember those. We got 3. Bring this down again. I'm going to replace the 2 with a 3 this time. And I got a 6. Well, actually, I bet we can do the rest right now. Look at this. 3, 6. Do we see a pattern here? I have a 3, a 6, a 3, a 6. This one's an 11. I bet this one's 11 as well. And we can check it. This is 3. 3 squared is 9. 9 plus 2 is 11. Ha! All right, let's get those points done. -1, 6. Good. 0, 3. 1, 2. 2, 3. 3, 6. And 4, 11. There we go. We can see the shape of our parabola, right? It's not a V. A V would come straight down like that. This graph is going to curl a bit, like so. And you'll notice I kind of use multiple little pieces to make it looking like a V or like a U. It's totally up to you. Some of you can just draw that in perfectly and it looks a little more smooth than mine. I found those little pieces just help me keep it looking nice. And then we, of course, are asked for the domain and range. The domain, all real numbers, no surprise there. Our parabola is always going to get infinitely wide. But what about our range? Well, what's the lowest this graph ever gets? Looks like the lowest it ever gets is right about 2, isn't it? And so we say that the y is above 2, but also equal to 2. Last one. You guys try this one on your own. I'll fill in the outputs once you guys get it done, and then we will talk about our shortcut and be done for the day. Ready, set, go. All right, you're back. So if you're looking for each of these, we have -5 plus 2 squared minus 3. Don't forget that setup, please. -3 squared is 9. 9 minus 3 is 6. Next one, -4 plus 2 squared minus 3. -2 squared is 4. 4 minus 3 is 1. See what I said about this being faster than a calculator? It really is if you practice your mental math. -2 plus 2 is 0. 0 squared is 0. 0 minus 3, -3. Continuing on, -1 plus 2 squared minus 3. -1 plus 2 is 1. 1 squared is 1. 1 minus 3 is -2. We already saw a -2. I wonder if this guy will be a pattern too. Let's see. 0 plus 2 squared minus 3. 2 squared is 4. 4 minus 3 is 1. Ha! I bet this last one's going to be 6, but always good to double check. 3 squared is 9. 9 minus 3 is 6. Yes, it is. Look at that symmetric pattern. The symmetry shouldn't be too much of a surprise because we've seen that parabolas are symmetric on the previous page. They will always have some sort of symmetry, and if you can identify that symmetry, it's going to make your life a lot easier. Now, when I was asking my students to do this in class, instead of me doing all of the work, I actually just asked them to describe this parabola. And so I didn't even look at their papers. So for example, I might have said, "Hey Jasmine, where's the vertex for this parabola?" And I didn't have any work on there. And Jasmine, or whoever it was actually really good about it. They said, "Oh, Mr. Grant, the vertex is at the point -2, -3. From there, I actually knew what the parabola looked like. Maybe not perfectly, but if you know the vertex of the parabola, you can at least get a general idea for the shape. Now, we haven't explicitly talked about the vertex of a parabola today, but we've talked about vertices or vertexes before. Do you remember when? Oh, that's right. We talked about them last semester when we were dealing with those linear absolute value graphs. Do you remember those? Our linear absolute value graphs made a V, and we said the pointy part of the V was the vertex. Parabolas also have what we call a vertex as well. And that's kind of weird because normally a vertex is two line segments meeting. A parabola is not a line, but we just make it work. And all of my students are pretty comfortable with the idea that this bottom point is the vertex of the parabola. Now, let's finish off this domain and range really quickly. You might notice a couple things about this vertex. First, when dealing with the range, y is greater than or equal to what number? Oh, -3. And isn't that number part of the vertex right here? Was that the same up above? 2. Oh yeah, that was the vertex, huh? And then also, when we had this guy, 0, wasn't the vertex at 0? Well, that's interesting. Coincidence? I don't think so. I think the second part of this vertex, this second number, is the y value. And because the vertex is, at least today, the low part of the parabola, that will always connect over to the range. But the second thing that should be interesting to you is that with this vertex, you should notice some sort of connection back to the original equation. Do you see it? 1, 2 in the original equation, -2, -3 in the original equation? I bet you do. We've studied HK form for a few months now, and we've discussed how the vertex relates to HK form. Does it look to be about the same here? Now remember, HK form really gives us a shortcut, a non-math arithmetic shortcut to find the vertex and to graph a function. And if you flip to the last page, we are going to go ahead and analyze HK form for quadratics. This unit, we're studying the form of a quadratic equation known as vertex form. There are actually 3 forms of quadratics, and we're going to be exposed to those as we move throughout the rest of this semester. Now, vertex form is really just a fancy way for us to say HK form. So let's go ahead and look at the quadratic vertex form below. And let's make sure we're comfortable with what each letter and number does. Well, we know that y is the output. It's the answer when you do all the math. And of course, x is the input. If you wanted the maybe fancier, more scientific names for these, we say x is the independent variable. Okay? And y is the dependent variable. Y depends on what you input for x. But then let's get to our shortcuts, and we don't need to go into them too deeply because we've done them before. We should remember that h, whatever this number is that we see here, shifts our parabola horizontally. And in fact, you can think of that's what h stands for. Reminder, horizontal means we shift the graph left and right. H is kind of like the x part of our vertex. K shifts our parabola vertically. And remember, I misspell vertically just because that way we get a K in the problem as well. And vertically runs up and down. But then, and this is very common, I'll get students that will look at a quadratic equation, maybe like this guy down here, and they'll say, oh, but wait, this says -2 squared. So does that mean I have to do negative 2 times itself? And my answer is no, because HK is actually a shortcut. HK allows us to get the vertex without doing any math. So then the students will say, well, what do we do with the square? Does it do anything? And the answer is yes, it does. The square actually tells us the shape of the graph. The square is what makes the graph a U, which is to say a parabola. If there was no square here, that's still an HK form, but now it makes what shape? Oh, that's right. It makes a line without a square. We did that last semester. So the square just tells us the shape. We don't do any math with it. Now, as a reminder, when we put h and k together as a coordinate pair just means x comma y, we say that the hk forms the vertex of the parabola. Also, word of warning, don't forget, h is still in the vertex the opposite of the sign it looks like in the equation. Now, for the rest of today, there's 5 questions left, we are going to sketch some very approximate parabolas. The ones we did on this page, look, we had 1, 2, 3, 4, 5, 6, we had 7 points. We are not going to create 7 points today for a parabola. We're just going to graph the vertex and then a parabola. That's it. And they're not going to be perfect, and that's okay. In fact, over the next couple of classes, we'll work on making more accurate parabolas. For now, though, we're just going to practice that HK form. So, for example, on A, they ask us to graph and then give the domain and range. So let's start with the vertex. Our vertex is the opposite of H, that's 2, comma K, which is negative 1. Right 2, down 1. From here, there is a square, so we know this makes that parabola, that U-shaped graph. So I'm just going to go ahead and graph my U-shaped equation. That's it. Nothing else. No more accurate than that. Our domain, of course, is still that all real numbers. You might remember that fancy symbol for all real numbers. It's that double bar R. So there's 2 bars down here, and then it's an R. It means the same thing. Nice way to be fancy, though. And then our range, we'll take a look at that k value. That's the lowest our graph gets. And so our range is y is greater than or equal to the k value. So go ahead and try these last 4. If you get stuck anywhere, unpause and skip to that part. And I'm excited to watch your success. Ready, set, go. All right, you're back. Let's finish these off. X plus 1 squared might give you a bit of trouble here, and that's totally fine. The reason it might give you a bit of trouble is because if you compare the equation to the equation up above, you'll notice that certainly we have an h value. That's in between the x and the square. And we know the h is the opposite, so that's negative 1. But the trick then is, what is the number adding after the square? Well, if we didn't write it, then what can you add that you don't have to write because it doesn't change the problem? Hopefully you said 0. Right? If you give someone $0, they stay the same. It's not a 1. If you give someone $1, now we've changed them. So, negative 1 comma 0 right here. And then our parabola. Nothing more complicated than that. Domain, all real numbers. And our range, the k value is 0. Y is greater than or equal to 0. Last graphing one, x squared minus 4. Now this one is certainly tricky. It always trips up my students for, not even today, but for weeks and for months. They get a little scared here, and it's not too bad. So looking at this, we have the x and the squared. And if you look at our HK form, the x and the squared are right next to each other in our problem. In HK form, there's an h in the middle of the x and the square. So h always has to come between the x and the square. So I'm actually going to rewrite this really quickly so that we can see there's a gap between the x and the square. And in fact, we usually put that in parentheses. I haven't changed the problem at all. This is still x squared. I just left an extra gap. And this allows us to see that then minus 4 is actually the k value. It comes after the square. What's hidden in between the x and the square that can be adding or subtracting? Well, it is, once again, 0. So getting this graphed, and this was the second thing that tripped up my students, 0 along the x-axis, so don't move left or right, but then move down 1, 2, 3, 4. Many of my students put this on the x. And then here's your parabola. We don't want that to curve back in, though. There's this. There's that. And we're good. All right, our last two problems today are really working backwards. We're going to give you a graph and then move it. And you're going to have to tell us where is the new graph. So if we look at D, we have this graph. Currently the vertex, use a different color here, currently the vertex is at 0, 0. They are telling us we are going to translate, which we should know means move, the parabola left 2 units, 1, 2, and then up 4 units, 1, 2, 3, 4. So I just moved the vertex point. You could move the other points too. For example, here is this point. I'll do it in blue. 1, 2 to the left, then up 1, 2, 3, 4. And here's another point on that same parabola. But I think if you just move the vertex, you could probably recreate this parabola no problem. It's going to be at this new vertex and in an upward direction. Then they asked us for the equation. Now for the equation in vertex form, we actually need the new vertex. So what are the coordinates? We moved left 2, so -2, and then up 4, which is +4. So would I do -2 + 4? Well, I don't think so, because -2, HK form is always the opposite. I think this has to be a +2 + 4. This square that's right here just tells us it makes that U-shaped graph. So 1 to go. All right, we currently have a vertex at 1, 2, 3, 4 at -4, 1, 2, 3. We want to translate or move this parabola right 30 units and down 70. Whoa! Okay, if we're going to go right 30 units, do you just want to sit there and count 30 to the right? It sounds pretty awful to me. But I think to move somewhere, couldn't we just take the -4 and add 30 units to it? -4 + 30, and that gives us 26. That would make sense, right? If you moved 30 over here, if you already have -4 to the left, you're only going to get over to 26. So this would be 26, something. But then we also have to move it down 70 units. Oof! If we're going to go down 70 units, but we're already at 3, wouldn't we do 3 minus 70? -67. That's going to give us our new point way down here. 26, -67. How do we write that? Well, we have a 26 and a 67. The k value is a minus. Easy enough. The h value is always the opposite, so it looks like +26. We'll put a -26. All right, so quick reminders. First, quadratic equations are created by a second common difference pattern. If you see a pattern that doesn't have a common difference, but then on the second level does have a common difference, we know that this is called a quadratic function. Now be careful, because just since the numbers are different does not make it quadratic. For example, if I had a pattern that went up by 1, and then by 7, and then by 100, and then by 50, and then by 12, that's not quadratic. The numbers are all different, just like these, but quadratic has to have a common second difference. The graph of a quadratic equation is a U, and we call that U-shaped graph a parabola. Once we have the parabola, finding the range isn't too hard, because the range is always the k value of our vertex. Speaking of that k value, the parabolas this unit are all going to be in vertex form, HK form, which we've done in previous units. HK form still has the opposite of h, k, and that is all we need to be successful on parabolas for lesson 7.1. Thanks for tuning in, and I'm excited to have you back for 7.2.